Okay, today we're going to talk about so-called positive definite schemes. What are positive definite schemes? As the name implies, the schemes that preserve the sign of your function or transported variable, for example. So let's say that we have an equation for some scalar phi. So there is this advection with velocity u, and also let's say that there is some diffusion. So this is pretty typical problem that we we deal with in atmospheric flows. So phi can be scalar, which is say temperature, water vapor, cloud water content, and so on. And for those quantities, it's very important to preserve the sign, or to preserve, more specifically, the positiveness. So temperature should be positive if it's in Kelvin, and water vapor and especially cloud water should be, of course, positive. So it is not automatic property. So if you use just any arbitrary scheme, a numerical scheme with some approximation in space and time, you may very quickly find out that in many cases you generate negative values even for quantity which is initially positively defined and your initial conditions are all positive numbers. But when you run it a little bit, then you have some problem, like in one of our homeworks when we studied some transport by Lux scheme, I believe, and we transported a so-called like cloud. So it's some signal that looked like that. And as time goes, you may remember that we actually generated for refrog, for example, scheme, that solutions that look like something like that. So here you have these negative values, and of course that would be a problem if you transported, say, cloud water with this scheme, and cloud water is indeed this kind of sharp, there are this kind of sharp boundaries when you have no cloud water and then suddenly you have this cloud. And so you should do something about that. Of course, you could just use simple fill-in algorithm. Like, for example, you just fill those values with zeros, but in order to conserve total mass, so you basically added some mass here, so you need to subtract some from here. And of course, from closer, but then the question is how you actually subtract it. There are some fill-in algorithms out there, and they're pretty messy. They can be pretty messy sometimes, and so in principle that could work. But there are better methods for that, for this kind of instead of using fill-in algorithm. There are schemes that actually, by design, they don't produce negative values in one time step when at the beginning of time step values are non-negative. Those schemes are called positive definite schemes. So positive definite schemes are a subset of so-called monotonic schemes. Monotonic schemes are the schemes that preserve minimum and maximum values over, say, one time step. So if at the beginning of time step you had this certain minimum and maximum value of your transported thing, then if it's like for transport itself, not for diffusion, transport itself does not change minimum and maximum values. Well, as the name implies, it just transports stuff. So So monotonic property means that minimum maximum do not change, and positive definite obviously is a subset of that, because if you have minimum value at the beginning of time step which was 0, it will be maintained being 0, so it will automatically be positive definite. But monotonic schemes are actually more complicated to program, to make, than just positive definite schemes. You can have very easily, you can have, and vice versa, like it's relatively easy to design positive definite scheme, but it would be much more effort to actually make that positive definite scheme also monotonic. And so you could actually, like in this case, you could produce solution that looks maybe like that. So it would be positive definite, but it would produce all these sort of oscillations nonetheless. And and those could be also problematic if you like transport cloud. You can generate rain, for example, here because your cloud water becomes too high, and so on. So just being positive definite is not sufficient to produce nice looking solution. So generally you need also monotonic scheme. But let's talk here for simplicity just about positive definite schemes. So various processes can be, again, arbitrary schemes may not be positive definite. But let's consider two different processes here separately. So let's first consider diffusion. So diffusion scheme. So we have, for diffusion, let's consider simplest scheme that we always use, which is second order approximation in space and first order in time for the diffusion operator. So basically we have like a scheme in one dimension. One dimension is like the following: fn plus 1 k minus phi kn divided by delta t. So this is our Euler operator, equals to this k k phi k plus 1 n minus 2 phi k n plus phi k minus 1 n divided by delta x squared. So this is our typical approximation of a diffusion equation with second order diffusion operator. Well, great. So is it positive definite? Does it preserve the sign? For that, let's write it in a slightly different form, putting all n plus 1 to the left hand side, which is just one number here, one variable here, like that, equals to phi chi kn plus k delta t divided by delta x squared, phi k plus 1 n minus 2 phi k n plus phi k minus 1 n. So now let's combine these index variables with index k. We have f phi k n plus 1 equals to k delta t divided by delta x squared phi k plus 1 plus 1 minus 2 k delta t divided by delta x squared phi k and plus k delta t no delta divided by delta x squared phi k minus 1 n. Great. So now let's see. Let's say that at the time step n, all our quantities phi are positive definite, so they all greater. So phi n k all greater or equal than 0. Then from that you see that this, so this quantity, this coefficient is positive, phi is positive or non-negative. So this one is not going to present any problems when adding to this result. It's with plus sign here. Now this guy is the same way, so they all contribute in positive way, adding. But this guy can become negative, because if this term here is greater than 1, then this term will come with minus sign here, and depending on these values, k plus 1 and k minus 1, this term can overwhelm those two terms and create negative value of phi in this grid point. So we conclude that in order for this scheme to be positive definite, for positivity, we obviously need that k delta t divided by delta x squared should be smaller or equal than 1/2. You can see that in that case this thing would be positive. But if we look at this condition, it is exactly condition that is condition for stability of the scheme. So same as stability criterion. So we conclude then that this simple advection scheme, I mean a diffusion scheme, is naturally positive definite as long as it's stable. So it's kind of interesting that actually, and that's basically interesting also that we know that diffusion cannot create, if your quantity is positive, diffusion cannot create negative quantities. All diffusion does is basically smear stuff around, but it doesn't really destroy stuff that it transports. It just basically distributes it. So it should maintain positive if you diffuse some, say, concentration of some stuff, then there is no possibility to generate negative concentrations in nature. And apparently this is also the same as true, that as long as stable, and stability means that this equation is actually consistent with diffusion, that otherwise this diffusion coefficient would be negative in a truncation expansion. So we conclude that this condition is basically manifestation of that for stability you need preserved positiveness. And that's interesting. So diffusion represents no problem for our equation here. It will preserve sign of any quantity. So it's positive definite naturally. Great. So now let's consider advection. Eraser, not good. Okay, so number 2, advection. So let's consider advection with some constant velocity c that we've done so many times before. So let's see that. Let's make c positive, so our signal moves to the right. And then first, let's consider first order upstream bias scheme. Upstream biased, or upstream biased. So we have scheme like phi n plus 1 k minus phi k n divided by delta t equals to minus c phi k n minus phi k minus 1 n divided by delta x. So you see we take this upstream derivative. So if you write again in this form, n plus 1 on the left hand side, the rest on the right hand side, we have the following, that it's 1 minus c delta t divided by delta x phi k n plus c delta t divided by delta x phi k minus 1 n. So now for stability, we remember for upstream bias scheme, we have a condition that c delta t over delta x should be smaller than 1. For stability. So this is current number should be smaller than 1. But you can easily see that it's actually, it is also required for positive definiteness. So you see that if this guy is positive, so now for this term to be positive, you need c delta t delta x smaller than 1, like our stability criteria. So again, as in the diffusion equation, we see that this first order upstream bias scheme is naturally positive definite. It will maintain sign of a signal. And that's great. Wouldn't be nice then? Why don't we just use it? And you remember that the problem with first order upstream biased scheme, that it has very large this implicit diffusion associated with it. So if you transport cloud like that, and as time goes, it will be like very smeared signal. So it has tendency to diffuse it too much, even though the equation itself should needs just to transport this this signal to the right with no actual distortion. So this scheme distorts the original signal too much. So that's why it's barely, it's seldom actually used. And the interesting thing that actually first order upstream bias scheme is the only one linear scheme, linear. So without all this if statements, some correctors, limiters and stuff like that, that actually natural scheme just from Taylor expansion, first order scheme that actually positive definite. The only scheme, only linear scheme. Scheme with positive definiteness. There are no other schemes like that, unfortunately. That's why we need to go through all these hoops to solve this problem for schemes that not that diffusive as this one. So this scheme is very rarely used in our field. So, so let's consider second order scheme. Like say refrog scheme. So refrog. So we can write it, well, refrog schema, let me remind you, it's the time derivative with second order approximated, and advective part, the space part looks the following. So this is refrog scheme, and it can be written in our canonical form, n plus 1 equals to phi k n minus 1 minus c delta t divided by 2 delta x phi k plus 1 plus c delta t divided by 2 delta x phi k minus 1 n. So let's see. If our scheme was positive definite or positive or non-negative at time step n minus 1, then this guy is positive. So you see it contributes positively to this. This guy is positive because phi is positive on previous time step, we assume. So this one no problem. But this scheme, this term
can be negative, because this is positive, and depending on these values of 2, this term can easily overwhelm those two terms and produce negative phi. So let's say that this guy is 0 and this guy is 0, but this guy is not 0, then it's automatically on this time step it will be, even though this one is positive, it will generate negative value here. So this scheme is not positive definite by no stretch of imagination. And we know that as from your homework, that it produces solutions like that with negative oscillations as well. So generally all advective schemes above first order are not positively definite. So we need to come up with some kind of way to fix it, and that would involve certain modifications to your original scheme that would basically put some kind of fixers in there. So scheme becomes nonlinear then. Nonlinear meaning that if you add constant to your function, just arbitrary constant everywhere is the same, it may change your solution. Even though if you add constant to this equation, to phi, it will just differentiate it up, be differentiated out. It won't affect the solution. Your solution would be the same as before, just also with added constant. But this nonlinear scheme, they have a tendency to modify the solution slightly in those places where this massaging of scheme is required to preserve positive definiteness of that scheme. So let's one of the workhorses of this business of making positive definite monotonic. We're not going to talk about in this lecture about monotonic schemes, but positive definite schemes, a so-called donor cell scheme. So let's consider. But first of all, just generally, the approach is use so-called equations in flux form. So advection in flux form, and we already considered that flux form when we talked about conservation properties. So advection in flux form would look like the following, like something like that equals to 0. Well, I don't include any rows there. We assume that rho is constant at 1. So kind of incompressible flow there for simplicity. So this is an equation in flux form. So basically it's an equation that written as some flux divergence of some flux. And in that way you can ensure easily conservation properties of phi when we discuss that in the corresponding lecture. So we can write this using second order approximation, like for example we have cell here, and this cell k is k minus 1, cell k plus 1, and so we define our quantity phi in this cell. So it's a similar approach as we used for finite volume in one-dimensional, but remember finite volume in one dimension is the same thing as finite differences in one dimension in flux form. So and here you define your fluxes at boundaries, which we denote k minus 1/2, k plus 1/2. So you have some your fluxes. Then basically what this says,
you approximated the following, that some diff f dt equals, we don't specify this particular derivative, but it's equal to flux k plus 1/2 minus flux k minus 1/2 divided by delta x k. So it's delta x, it's this distance. So it's your cell's width. So that's basically so-called like this equation, a finite volume equation basically, or finite difference equation in flux form for this problem. So now we have these two fluxes, and you can see that it all depends, the positiveness of this quantity depends on how you define those fluxes. So some fluxes can be adding to that cell. This, let's call phi is a mass. So it's adding some mass, and fluxes that go away, they would subtract that mass. So as long as the sum of those two fluxes that add or subtract on those boundaries add up to positive quantity, then mass cannot be negative. But if it subtracts too much mass, more than this cell contains over one time step, it will generate negative value. So we need to come up with some scheme which is which kind of controls those fluxes such that phi is actually preserved. There are many approaches to that problem, very many approaches. And here today I will talk about one specific approach that's kind of easy to understand. It's called the donor cell approach. So donor cell basically defines those fluxes. So those fluxes should be some velocity times phi. So in donor cell approach, you say, okay, if, for example, some flux, if u is, for example, on this boundary, if u is kind of bringing new stuff to this cell, then you only bring value of these values of phi in this cell. And if it leaves this cell, it's only flux is based on value in this cell, and so on. So it's kind of logical, but unfortunately it's only first order accurate, right? So you basically say that flux at k, say plus 1/2, so on this say boundary equals if so equals u k plus 1 f, or k plus 1/2 phi k plus 1 if this u k plus 1/2 smaller than 0. So when stuff is, so here is phi here, so this is k plus 1, k minus 1. So this flux k plus 1/2, it's only if velocity is looking this direction, so it's based on the value of this. And otherwise, it's k plus 1/2 times phi k. So if velocity is actually leaving this cell, it's only getting the value of phi with it. If u k minus 1/2 plus 1/2 greater than 0. If it's equal to 0, flux is 0, nothing really happens. Okay, so this is a donor cell. So basically, this cell is donor for this cell, and this cell is donor for this cell. That's basically why I assume why it's called. And now if you
you can easily then now see that the only way when phi can decrease if when stuff is leaving this end, it's based on this phi, and of course it depends on u, and then it of course should depend on the amount of time the stuff actually it takes to get rid of that phi. So this flux actually, so you need some if statement. So in the code, you're like computing those fluxes, and then you have some if u is smaller than 0, then you compute flux like that. If it's greater than 0, compute flux like this. So if statement sometimes, it depends on architecture, can be time consuming because you do these if statements in each iteration of your loop that you go through your grid, so it can be expensive. So depending on again architecture, it's not always true for all computers, but you can actually replace just some kind of hack here. To avoid if statements, you can write it as the following, as uk plus 1/2 plus absolute value of uk plus 1/2 times phi k plus uk plus 1/2 minus uk plus 1/2 absolute times phi k plus 1. So, so you could actually easily see that when uk plus 1/2 is greater than 0, then this term will cancel, and then it will automatically compute. Well, of course, it should be 1/2 here. Then it will automatically, this term will drop out, so it will be this expression, and if velocity is negative, then this term will drop out, and this actually will be equal to this. So, so everything works kind of fine. So this one avoids if statement altogether, but actually computing absolute value and additions and all this stuff also takes some time, but so you need to test which one is actually faster. In my experience, long time ago on a previous, I don't know if it's today it's true. I always use this formula. I don't use this if statements, and it was actually I tested it. It was faster than this one, but again it depends on it depends on architecture. Okay, so so this is a donor cell. Let's check it for some situations. Is it positive definite? That's what we're trying to establish here. So we can so we write the following. Let's write this donor cell scheme in a full form as we did before, with n+1 term on the left. So we have situation, one situation, let's say that u, write it. So case 1, when uk k minus 1/2 greater than 0 and uk plus 1/2 is smaller than 0. So remember, the sign of f is determined by use because phi is always positive. So then we have our equation can be written as the following. So using this kind of like current numbers, phi k minus 1 minus
uk plus 1 half delta t delta x phi k plus 1. So now, so our case is when this velocity is going into the flux, into the cell, and this velocity also going to the cell. And of course you expect that in this case phi will be it's always added mass to this cell, and which means that this cell will that this value of phi will be preserved. So which let's check it. This guy is greater than 0. This guy is greater than 0 because this u is greater than 0. And this u is smaller than 0. That cancels this minus sign. It's also greater than 0. So it's preserved sign. So this is case of convergence into the cell. So phi k n plus 1 is greater, is always will be positive definite. So now let's consider case 2, which is extreme. We won't consider all 4 cases that are possible here, but consider the worst case scenario. Case 2, worst case scenario. It's when there is convergence away, there is divergence away from the cell. So in that case, your uk minus 1 half is negative, and uk plus 1 half is positive. And it's very easy to see that then your scheme would look like the following. And so now you see they're all phi k. So this guy is greater than 0. Now this phi k is greater, so this k minus 1 is smaller than 0. So this one can be smaller, it's smaller than 0. And this positive with minus is also smaller than 0. So those both two terms trying to kill this guy to produce negative values. So how to avoid that? Obviously, we need that as a condition that some maximum of u k delta uk plus say 1 half, because or minus 1 half, doesn't matter, delta t divided by delta x, or on everywhere in the grid, should be smaller than 1 half. If you do that, then it will guarantee that your scheme will be positive definite. And this condition looks like stability condition, right? But for stability, for this donor cell, actually, stability of donor cell, it's actually based on, if you actually look carefully to it, it's based on first order upstream bias scheme, except for that it's written in flux form. And as a result, you have this actually more stringent criterion. So it's actually more restrictive than stability. More restrictive than stability. Stability criterion. But so this scheme is good. This one is a little bit unfortunate, but it happens could happen relatively rarely. So you can actually still run with this condition, stability condition. And so sometimes, and then just basically fix it, because it maybe doesn't happen very often. Fix it just by making it negative values, making them positive.
but the main thing about it, which is not nice, is that it's first order accurate. It's a first order scheme. Order accurate. First order truncation. So it will be diffusive. So very diffusive scheme. And that's sometimes not very not very desirable quality of the scheme. So can we fix that donor cell scheme to be higher order accurate, higher than first order, but at the same time still be positive definite? And actually, yes, there is such a very simple approach called anti-diffusive velocity approach. So basically, it's using this fact that we already established that diffusion operator or diffusion term is naturally positive definite. So our donor cell is from our previous lecture, we know that first order accurate scheme and donor cell scheme is basically variation of flux form of upstream bias scheme. So it's equivalent to their, so donor cell is equivalent to this following scheme. So you have advection in flux form, but also you have diffusion with some coefficient that in this case, because it's not constant C as we used before, so if you do Taylor expansion or in this form, you will arrive to this diffusion or implicit diffusion terms like that looks like this. Implicit diffusion or numeric diffusion or numerical diffusion. I'm sorry that sometimes I kind of go at the angle, because when you're standing like this close to the board and you write it down, actually everything looks straight from your perspective, but from perspective of camera, like I have tendency to move down as I write it. I will try to maintain it straight, but we'll see. So where K, this diffusion coefficient, equals to 1/2 U absolute value delta x minus U square delta t. So this is implicit diffusion coefficient. So basically, instead of solving just this equation equal to 0, we add this implicit diffusion with diffusive coefficient that look like that when we use this donor cell approach. Wouldn't it be nice to basically that diffusion term, that what makes our solution, instead of looking like that, looks like that. So basically diffusing it out. Would be nice to just be able to subtract this implicit diffusion. Why don't we just put a minus sign in here? We actually did that approach. It worked in case of Lax-Vendrov scheme. In a way, we're kind of subtracting this diffusion, but the problem is that diffusion was already with negative sign. This implicit diffusion was with negative sign, and we actually added explicit term with diffusion, and it looked normal with positive sign. So mathematically it was okay, but that term canceled that truncation negative diffusion term. That's why it works. But in this case it's opposite. That implicit diffusion is already in normal positive term, and if we add explicit term diffusion term that would cancel that implicit diffusion term to avoid this kind of broadening of your signal, that would be unstable from the get-go, because diffusion cannot have negative diffusion coefficient. So we cannot do that. We cannot just subtract it. Fortunately, there is another approach that was first proposed by a very good applied mathematician, one of the best ones out there, practical kind of applied mathematicians. It's Piotr Smolarkiewicz. So it's he's like Polish guy, so his last name, like all Slavs, kind of tend to be long. So in his paper in like 1981 or 83, so he proposed so-called anti-diffusive velocities. Instead of diffusion, why don't we convert diffusion into some advection with those anti-diffusive velocities? And velocities can be positive, negative. Stability only depends on some kind of local current number, but you can make it them any sign you want. So you need to compute these anti-diffusive velocities instead of diffusion coefficient. And for that, let's consider this term separately. So we have ddxk d phi dx, and we will use this fact that phi is not negative here. In that case, we actually can do that. So basically, let's rewrite it the following way. d dx. Now let's multiply it by phi and divide it by phi. So we have like k 1 over phi d phi dx times phi. So it's all under this d dx. So we didn't change anything. What we did is just multiply by phi, divide by phi. So now let's define this quantity as anti-diffusive velocity, because it does look like convergence of a velocity flux. So it's called a diffusion velocity, udiff times phi. So it looks exactly like this term now, just different u. And now this u, we can actually it can be positive, negative, whatever we want to basically reduce this diffusion problem of our donor cell. So so this u is this is how it's computed. We know k, and we know this expression, and this is why you need actually phi to be positive definite for it to work, because otherwise, if it's not, you have this difficulty that you may actually divide by negative numbers or by zero. But if it's always positive, in those points you only apply it where phi is positive, then you can actually diffuse it back by subtracting this term from your equation on the right hand side. So basically, you solving the following equation instead of equation like that, you should solve the following equation: minus d dx u minus u diffusion phi. So this modified equation. So you see that this is basically the approach. And how you do it in practice, first you use donor cell scheme, and you use this anti-diffusive velocities as some kind of iterative procedure. You don't compute it right away. You could, for example, use just forward in time scheme, because donor cell can work with forward in time scheme, because it's just based on upstream bias scheme. And you remember that earlier
time differences works just fine with upstream bias scheme. So forward in time Euler scheme can be used here easily. So so first step, you just solve your equation without antidiffusive velocities. Second step, you compute antidiffusive velocities as let's call it adiffusive, anti-diffusive, equals to minus. So let's define it like with plus sign here. So then it's going to be minus u k plus 1/2. So it's k plus 1/2 because we need it for our Donald cell at those points. Delta x minus u k plus 1/2 squared delta t divided, so you need, this is your k, by divided by phi, and make it like, let's make it symmetric, k plus 1 plus phi k. So it will take this 2 here, and plus epsilon, just to make sure that if those two guys are zeros, then you won't divide by 0, where epsilon is small, say 10 to minus 9, let's say, small number, times phi k plus 1, this provisional solution. So first you solve for this provisional solution. Minus phi k. So this is how you find your antidiffusion velocities, and then you solve it again, but replacing, you can do it like that, or do it like double star or whatever, but over t minus d dx u adiffusive times phi. So you now use donor cell to solve this equation, using now these velocities, not these velocities, the original. And you can actually do it several times. You can do it like twice. First you compute antidiffusive velocities, then you compute this kind of compensation of or reduction of this diffusion error. Then you compute another antidiffusion velocity based on that, and then you do it again. And that actually been demonstrated that it improve your solution. So as a result, your solution would not be this diffusive as with using donor cell. So the advantage of this approach uses a simple donor cell as your base. You use first order in time mathematics. Actually here you can use semi-implicit scheme if you want, because if you this one is can be one no, actually not here. Sorry. Your velocities can be here as n plus 1/2, so presumably you know your velocities at time step n plus 1, so you basically average it in time. That would increase accuracy of your transport, because your velocity will be kind of on half time step instead of just on n, you use n plus 1/2. And so overall this scheme is going to be second order in space. So this one is second order truncation. So that's the essence of this antidiffusive scheme. The problems sometimes arise when you go when you move to 2 dimensions. So in 2 dimensions you use donor cell again in 2 dimensions at once. So you can use all your fluxes in x and y directions. But the problem is that antidiffusion in 2 dimensions, in addition to these terms like d dx, k df dx, should be of course d dy k, so diffusion in y direction, but also there are, if you do Taylor expansion, there are cross terms. So in 2D there are there is cross diffusion. So terms like d, dx, k, some different k, k star, d, phi, dy, terms like that. And those you need to also include in this approach. So you compute antidiffusive velocities also based on these cross terms, which are done similarly to this, just slightly different formula. And if you're interested, you can find it in small archivage papers. But so that's called cross diffusion terms, and they need to be included, otherwise the scheme may be unstable. So you need to add them too. And if you do that, you will produce very nice, beautiful two-dimensional solutions that very minimally actually distorted by advected around the grid. There are even, again, this one is positive definite scheme. There are so-called monotonic correctors for that scheme. Monotonic correctors are basically, it's even better way, does not produce new maximum and minimum. This scheme does not produce new minima, which are 0, but it can produce new maxima, this scheme. It can actually produce some phenomenon like that. But monotonic corrector would take care of that. Yeah, I'm not going to talk about that corrector in this lecture. So that's basically what I wanted to say about positive definite schemes. There are other approaches to this problem, so-called flux corrected transport schemes. Basically, the idea there is to compute fluxes using high-order schemes, high-order truncation, not donor cell, but some more kind of using more grid points. And in that case, you can obviously produce these oscillations that can be negative, and then you use correction of those fluxes, and there are many ways of doing so. And that's why I'm not going to talk about particular one, because there are so many ways. You can come up with your own if you're creative enough. So I'm not going to kind of pay too much attention to particular way, but that's basically the idea of flux corrected transport. Or there are also so-called flux limiters. So you basically limit the flux to avoid your problems, for example, to maintain monotonicity or positive definiteness just by limiting certain fluxes. Those schemes can be a little bit expensive. Even this scheme is more expensive because you basically, it requires 2 or 3 times more computer time than ordinary donor cell, because you need to compute these antidiffusive velocities and apply the scheme again. So those schemes, flux corrected kind of schemes or anti-diffusive schemes can be quite much more expensive than linear schemes like donor scheme. But sometimes there is no really other option. You need to maintain positive definiteness and conserve mass at the same time, or conserve total integral of mass of transported stuff in your model, like water vapor and cloud water. Obviously you need to conserve mass, otherwise you may have some lots of problems in your simulation. So sometimes you just don't have choice. You need to choose some positive definite or monotonic scheme that that can be quite expensive again. Okay, but we're not going to talk about that in this class. I think it's too specialized. There are many approaches. Okay.